This first video on volume of solids of revolution, we're talking about some background information, linking it to the calculus that you already know, and we're looking about rotations about either x or y axis to produce solids. So what if we had to determine the volume of this glass here, and we only know these measurements? We'd probably have to make a few assumptions, perhaps that the this profile down the side here is a straight line. That might be reasonable, and we could use an approximation method. We could say, well, it's we could use a bunch of cylinders. Okay, so there's one there, but you'd have to think, how thick would I or high would I make these cylinders? Okay, and that drawing's a bit lumpy, I'm sorry about that. But you'd have a bunch of cylinders. Of course, as you appreciate, that's not going to be accurate because a cylinder has, or a disc, looking at it from its side, it has a vertical height, and this glass I should say, is coming out at a slight angle, and so you're going to have some error every time you use a disc there. Of course, the more discs you use, and the thinner they are, the less area, and you know this from your previous studies. So there's going to be some error, but because we know calculus, we can find a precise way of finding these solids. And we can apply that to determine things like volume and capacity of solids. In the past, with our calculus, we've looked at the area under a graph, such as this example here, y equals x squared. And we looked at it in terms of the concept of the limit of a sum. So that means if we have n subintervals, so the interval is from 0 to b in this case, and so it's split up into smaller intervals called subintervals. We have n subintervals, and basically each subinterval is the base of a rectangle, as you can see, and the height is determined by, depending on what method we're using. In this case, it's the right hand ordinate, or the height is determined by the right hand point of contact with the curve. Of course, you might have seen other variations on that when it's left hand or middle. We've seen in the past, as n approaches infinity, as we get many strips, the strips become very many in number, and they become very thin. And the limit of that is where we have the exact shape, okay? By having very many strips, as n approaches infinity, and having very thin strips, it reduces the error down till it becomes 0, and we have the actual area under a curve. Now this video is about volume, so we're getting there. We can apply that same idea in terms of volume. If we have this shape here, you can see right there, it's sort of like a flask sort of thing, but it's a bit bumpy. We've got a solid there, and we've got the thickness of each slice called delta x. Okay, so where delta x is a very thin slice. Okay, so very thin, just like the strips were very narrow before. So the width of that slice, or the thickness of it, is delta x. So the volume would be the cross-sectional area times delta x for each of those. Okay, so A times delta x. Of course, A is changing. It's changing often as a function of something, and especially in the tasks we look at. So we could use sigma notation for the total volume would be all of those slices together. So from A through to B, we've got, using our sigma notation, x equals A to x equals B, and it'd be A. all the cross-sectional areas times all of the delta x's. Now, just like with the area under a curve, we can use an approximation technique, or we can find the limit of the sum. So basically, if we've got a similar function here, we've got half x squared this time instead of x squared, because x squared was just vertically, it posed some challenges in terms of fitting it in on the screen. But if we've got, you can see there, when have a close look, you can see the rotation. Alright, so we can get that by rotating a series of strips around, creating discs or cylinders. And if we use the limit idea from calculus on that, you'd see we get thinner and thinner discs, more and more discs, and less area, and a more seamless result. So if we increase the number of discs like that, you can see between the interval, I might make that a little bit bigger, there we go. So you see that it gets smoother and smoother, and if you reduce the number of discs down, it gets cruder and cruder, very crude at the bottom end. So that's the concept behind it. A key example of this would be the volume of a sphere by rotating a semicircular area around an axis. For example, like this, if we were to do this with the x-axis for this semicircle here. Okay, so we could get that by, if we have the as an example, the function for the semicircle's line. Yeah, if it was, say, 4 minus x squared, like this example, square root 4 minus x squared, we could rotate that around and produce a solid, and that solid would actually be, from that semicircle, a solid would be a sphere. Now you know from junior maths that the volume of a cylinder is pi r squared h, and basically if we look at where would the cylinders be, or discs, they would be perhaps like this. Now essentially we're trying to make h approach 0, and then we're taking the sum of that, which would be an infinitely many bunch of discs or cylinders, and they'd be varying ideally according to that function for a semicircle. So they'd be varying laterally according to that function, because the cross-sectional area is varying, and the cross-sectional area of a cylinder is a circle. If we summed all these together, we would get the volume of the sphere. So importantly, when we rotate a region under a graph around an axis, we get the following results. Now this is a region between a line and an axis, not between two lines, because a future video will look at rotating a region between two lines around an axis. That's further down the track, that's not covered in this video. But between a line and an axis, now we need to know it for the x-axis, the volume of revolution of a solid that you get by rotating a line. The region between a line and the x-axis is given by the top there. So notice how it resembles that pi r squared from the you can see that squared effect there from the cylinder formula we just saw. And the dx, of course, is through all the calculus we've looked at, is the actual thing that's analogous to the cross-sectional, the delta h, the height, or delta x, as we were looking at earlier in the video. So essentially we're taking the integral of y squared dx, so we need to sub in that y as a function of x. It is squared. Pi being constant, we can take that out the front. Okay, that will give us the volume of revolution of a solid. Now likewise we can take it around the y-axis as well, and I'll show you one of those. In the second example, we are basically, just because I like things consistent, I'm going to make that a square bracket there. We do the same thing, but it's x squared dy. Okay, now I need to show you how to do that later in the video. So two examples where we've got a triangular shape. Okay, this region here is getting rotated around the x-axis. And what is the volume of the solid of revolution? So on this one here we need to know what the interval is, and it's between 0 and 2. It's because we have a line y equals 2x, and we can easily find that point of intersection. So we're going between 0 and 2, and we can put pi out the front there, and we have f of x, which is the governing function, so that's squared dx, and I'll just scroll down so you can see how that relates to the top formula there. Okay, so we go ahead and evaluate this. I'm going to square it first. So we've got essentially 4x squared dx there. And we go ahead and integrate. Between 0 and 2. And we get 32 pi on 3 cubic units. So cubic units because it's a volume. Getting back to our glass that we looked at earlier on, we could now use this approach on the glass, but firstly we have to work out what sort of function or shape has been rotated about what axis. If we label these points here for convenience A and B, and we put in axes, I must be careful here, I was about to say, but please forgive me for the wonky line. It would be convenient to have another axis come through here in line with A, like so. So what we are doing is rotating line, straight line, assuming this glass is apparently straight along that profile, we will be rotating that line AB about the y-axis. And that will rotate, creating the glass you see, or creating a volume or a capacity of the glass. The glass is not a solid, but the volume or the capacity of the glass is a solid space. Now I shouldn't have said that. That's quite funny. But it creates a continuous volume inside. If we're looking at the capacity of the glass, we are not calculating the volume of glass required to create this receptacle. We're looking at the capacity of the glass, so therefore we want basically a volume of revolution of a solid. So what we need to do is determine some points so we can come up with a line for AB, and we can use some points based on the dimensions given, and if you pause it and take a closer look, you'll see where those points come from, and we can do that fairly easily, and we can come up with the gradient for that line, and then using the point gradient form or otherwise come up with a linear function. Okay, and the linear function for AB is 11x take 55 on 2 if you use axes as I have. So the formula we want is pi times the integral from a to b of x squared dy. Now because it's dy, we could actually put in these limits here, and the y values are 0 and 11. So we're going between 0 and 11 x squared dy. Now we've got a function in terms of y. It might be good to have the function written in terms of x, so we can square x. So from here we need to rearrange to find x, or in other words f of y. So how do we isolate x? Well, we could go y plus 55 on 2 over 11 and then simplify all that there, and that'd be y on 11 plus 55 over 22, or just 5 over 2. So x, or f of y in other words, is y on 11 plus 5 over 2, and that's what we need, because remember this x squared in the formula is called f of y squared. So I guess we could write down what we're going to do now. Let's get that out of the way. We have 11, 0, and we have y over 11 plus 5 over 2 all squared dy. We can continue down below here, and basically using a form of integration we've learnt, we can get the following, and then we make the substitutions in and evaluate. We get 1199 pi on 12. If you want a practical answer, that's approximately equal to 314. The units given were centimeters, so centimeters cubed, which is equivalent to 314 milliliters for that glass, which seems pretty reasonable. And just to save the length of the video, obviously there were some steps there that based on the fact that the integration is prior knowledge for us, so it's assumed knowledge, you may need to go through and fill out some extra steps there. So that's the volume of solid of revolution video 1.